All right, so let's get started. So hopefully this doesn't cut out for some reason. The local connection is not working today. So where we left off before, we just introduced the Metropolis Hastings algorithm, which is an algorithm for, it's the first algorithm for Markov Chain Monte Carlo. So, I'll just mention again, Markov Chain, MCMC, Markov Chain Monte Carlo. And this is the so-called Metropolis Hastings algorithm, which is basically the steps here, which we ended on last time, is you generate some arbitrary high-dimensional vector. I'll just put a little vector symbol over it. So, and then you have some proposal density. So you can, I'll say, and some proposal density. G of y given x, which is often just whatever the initial x value is plus some zero mean Gaussian noise. So this is an example. And then that generates a potentially, so I mean, I guess I could make this just show this as a vector here, and this would be multivariate Gaussian. And so this moves you from your arbitrary position to some new position. And then your question is, do I stick with this new position? The goal here is to generate samples for someone for some useful purpose. And we'll talk about what those useful purposes might be. And so the question is, do I give them this sample or this new sample that I just perturbed? So, and that's, so that I generate the new sample. So this is the next candidate, which is, let's say, y is equal to g of x0. I'll say y is distributed according to g given x0. So there's some distribution here, which might just be this multivariate Gaussian centered around the original x position. So I just take a step in some random direction, and then I need to say, do I want to keep that or not? So I calculate this acceptance ratio, which is this fy divided by fx0. Little vector signs over both of those, which is just a likelihood ratio. When you consider f to be a probability density that you would like to sample from. And so I'm saying that I would like to sample from f. I have a potential sample in x0 that I was going to give, but now you've proposed y, is should I give y instead? And so if this acceptance ratio is greater than or equal to 1, then you accept y instead of x. Otherwise, you can accept y, but you do it with a probability which will be with this probability. So otherwise accept y with probability fy over fx naught. And then if y rejected, take your x instead. And then you can repeat back to number 2. And so this generates samples that are, after some initial transients die out, are guaranteed to come from this distribution F that you've put in here. And so I'd like to sample from a uniform distribution. Well, you could put a uniform distribution in here. I'd like to sample from an exponential distribution, where you could put an exponential distribution in here, and so on. And because this is a multivariate here, you could do things like define it as a distribution of some function of this state. And so the Metropolis part of it, so the original Metropolis version, basically said that F, that you were trying to sample from, was the Boltzmann distribution, which is, I will say, is proportional to an exponential of the energy of the state divided by this KT thing that we'll talk about as we get into simulated annealing. So if I want an exponential in terms of energy, then I can sample from a high dimensional space, and my samples will be from that high dimensional space, but I'm guaranteed that after some initial time, that those samples will have an energy profile, if I were to bin all of their energies, so that they fell right along an exponential. And so that was the original purpose of this, is that Metropolis et al. Wanted to draw samples from this Boltzmann distribution, which we talked about as being a special distribution in physics. And Hastings wanted to generalize this to any distribution, not just a Boltzmann distribution, and realized that you could replace the thing that Metropolis put in here with just this likelihood ratio, and the whole thing still worked. So that, yeah.
Is this also called the acceptance rejection algorithm?
This is a version of acceptance rejection algorithms. So there are a wide set of them that have to do, that all fall under this MCMC. So the downside of these algorithms is that they generate samples, but those samples are not guaranteed to be independent of each other. So if you know that, like if I had a sample X naught and I have a small proposal density around X naught, then I know that X and Y, if I accept Y, Y is going to be pretty close to X. And so samples that are near each other in kind of sampling time are likely going to be predicted from the previous sample. And so that could be a downside of these methods. And so if you want independent samples, you often have to waste a lot of samples, because you might need to go 10 samples or 100 samples in order to guarantee that that sample not only comes from the distribution, Gesundheit, but is independent of the other ones. So this is kind of an important point, is that like when we talk about white noise, like a lot of people talk about zero mean additive white noise, zero mean Gaussian additive white noise. The Gaussian comes from it having the right distribution, but the white comes from every sample being independent of every other sample. And so you don't get whiteness out of this. You don't get independence out of this automatically. You might have to do additional work to get that. So that's the downside of these approaches. But we'll talk about the upsides of these. But are there general questions about roughly, without worrying about, and so again, we'll get into applications here in a second, and then how this relates to simulated annealing, but just this general flow of the algorithm. Are there questions about this? You see what's going on here. Draw a random point, yeah.
So right now we're just generating samples, but are we doing anything with those samples?
Well, so you can do lots of things with samples, and so that's kind of so as an example, you can do anything with Monte Carlo sampling. You might want to, so let's just talk about applications here. So I'm going to swipe to the next page here, so like possible applications. So it is a Markov chain Monte Carlo. The Markov chain just comes from the fact that the next sample depends upon the previous sample. And so you build a Markov chain and it hops around the Markov chain. But it is still a Monte Carlo algorithm, and the Monte Carlo algorithm means that we're going to get lots of samples out of them, and we're going to make use of the distribution of samples that comes out of this thing. Now, you can have just Monte Carlo, in which case every sample is independent. The Markov Chain Monte Carlo, basically you're saying we're going to give up independence, but hopefully we get something out of that, which we'll talk about here in a second. But anything you can do with a Markov chain, you can do in theory with anything you do with Monte Carlo sampling, you can do with Markov chain Monte Carlo sampling, maybe protecting for this independence issue here. So, as an example, if I want to calculate, well, I know from the law of large numbers that if I take the sum, if I take a bunch of samples from any data set, then the sum, the sample average of that thing will end up approaching the integral where this is the PDF of the sampling distribution. So if I have some function like, let's say the function is the political party of a particular individual. And I would like to know what is the average kind of political, the average value of the politics of an area. Well, I know that if I sample from a particular area and I take the average there, that thing will converge over time to an average which is being taken over the density of the sampling distro. So my sampling distro might be just in a particular area. So that particular area might be more Republican or more Democrat or more Libertarian. And so the sampling distro really matters. If I sample uniformly, then I get a very different result than if I sample in a directed way. And so if I am interested in, so I can make use of this by saying that that if I want, so let's say I say, well, for simplicity, I would like to know the average value of f, and so I'm going to sample uniformly so I'd like to know the average value of this f, and this f is just a function. And I know that my x values are distributed according to some density function. So maybe just for, I'll just use g or maybe h in here, and this is just some density. So I would like to know what is the average value of my function given that my x values come from some distribution here. Now, one thing that I can do is use a sampling distribution which is uniform. And if I do that, then what this tells me is these densities will just turn into a constant, which is just going to put a scalar out front here in front of this mean. And as long as I divide by that scalar, then I can sample uniformly throughout the space and get a good estimate of what the actual average is subject to my real density. But I might have to do a lot of sampling because some of my uniform points might be in regions where there's actually very low density. So if I could just sample from the density that I'm interested in, I don't have to rescale things. So if I'm interested in the average value of something subject to a density, or any function of something subject to a density, I need a way to sample from that density. And so that's what these sampling functions provide, is a way to sample from densities. So that's the kind of statistical side of things. I might just want to build a simulation model. So if I want to do simulation, I might have built a model of arrivals into a doorway, or arrivals to an intersection, or a wide variety of things I've modeled in a probabilistic way, and I want to run a simulation over time. So each time I want to draw from that model. And so I need a way to draw from that model. And these MCMCs say, well, if you give me a density, I'll run my MCMC and it will give you draws from that model. So every draw is like a real data point that you could have gotten from the real world. So, draws from stochastic models And this is where things get interesting in terms of MCMC, because sometimes I want to build a stochastic model. And if I were to use a normal Monte Carlo approach, I would need to know the density normalized to a real probability density. And so in other words, if I think about a real probability density, f of x, then it has to have the feature that the integral of f of x dx is equal to 1. It has to have an area underneath it equal to 1. Now, a lot of times if I'm building, let's say I'm building a complex network model of, like, say I'm building some stochastic model of water as it flows throughout a network of tributaries and such, and some of it gets, it washes, not all of it stays in the stream. You pick up more water, you drop more water, so there's a lot of stochasticity in it. I want to know how much water I have at any particular point in the stream. Now, I might be able to write the physical relationships telling me how much water is coming into the stream and out of the stream and so on and so forth. And that tells me what the shape of these probability density functions are. But then in the end, after I build this shape here, in order for me to put it into most Monte Carlo algorithms, I would need to then normalize, which means taking an integral under some ugly thing. And it's possible that my density function isn't even analytically, isn't something that I can write down on paper. I have to execute a computer program to analyze it. So it may be that the shape of f of x may only be expressible as, I'll say, computer code. So then you could say, how do I normalize for an MC Monte Carlo sampling? And the beauty of this particular Markov chain Monte Carlo is that because it uses a likelihood ratio, you don't actually need to normalize any of your density functions. So because of that, and I'll swipe back to this, because we're using this here, I actually don't care if the density that's going into the Metropolis Hastings has an integral underneath it equal to 1. Just so long as it's positive, basically. As long as each one of these things is positive, that's all that matters. And so when if I build models that I know that in principle, if I did a complicated numerical integration, I could turn my computational model capturing the relationship between different outcomes. I could normalize all of them properly, but I don't need to if I'm going to use Metropolis Hastings, because it just looks at ratios, the likelihood ratios. So, to make this a little more concrete, it's kind of like if I had a number of discrete outcomes, I could computationally say that, so as an example, this is a little bit of a contrived example. Imagine you had 3 outcomes, A, B, and C, and whatever the probability of going to these outcomes was determined by running some computer code that ends up telling you the ratio that, well, I want B to be twice as likely as A, and C to be 4 times as likely as B. Well, you could do a little math and then figure out that, okay, if B is twice as likely as A and C is 4 times as likely as B, I can figure out what probabilities to assign to each one of these to guarantee the probability of A plus probability B plus probability C equals 1. But what the Metropolis Hastings algorithm does is it says I only need to know the relationship between A, B, and B and C, and A and C. I actually don't care that the probabilities you give me add up to 1. So you could just put integers in there. So I could say, well, I'm going to put in quotes around it, the probability of A is equal to 1. The probability of B is equal to 2. Put a little quote over there. And the probability of C is equal to 4. Now, if I look at this for this discrete problem, it's clear that if I would have just added up 1 plus 2 plus 4, I get 7. If I divided them all by 7, they'd be real probabilities, and they'd add up to 1. But I can skip that step. If I if somehow in my modeling approach, all I know is that this outcome needs to be twice as likely as this outcome and 4 times as likely as this outcome, that's all I need to put down here, and that's enough to make the Metropolis Hastings work.
So you only care about the proportionate relationship between.
That's what that in the Metropolis Hastings, it will guarantee that it will sample from a density, even if you don't give it a proper density, you just give it a density that's the right shape, that is proportional to the correct density. And that's that's a powerful feature of any MCMC algorithm that uses a likelihood ratio, is it gets rid of that dependence. And that is particularly important if you're doing any Bayesian inference. And so, so I'll just mention this on the side. For Bayesian inference, I don't know, so how, does anybody, so could somebody explain to me what Bayesian inference is? What might I mean by that? Or Bayesian estimation? What are you estimating, and how is that different than estimating in, you know, the normal way?
Posterior.
What do you mean by posterior distribution?
Normally we just calculate the prior probability or the given ratio, but by using the kind of information we can calculate posterior probabilities.
Posterior, but so it's, I feel a link to distribution here. So like, the idea here is if I get a bunch of data, the old school way of saying I have a bunch of data and I want to estimate what is the temperature in this room. Well, I could take a bunch of data and I could estimate a single temperature. And that would just be a point estimate. And I might be able to put confidence intervals around that. And that kind of got as fuzzy as we would get in the old days. Nowadays, we sort of say, well, ahead of time, I know that the temperature is probably no colder than it is outside and no hotter than something, you know, and it's no hotter than the surface of the sun, but I probably have more information than that. So I can put some priors on that. And a Bayesian approach says, can I take that distribution and add a little bit of mathematical info and shape it into another distribution? And instead of giving you a point estimate, I'm going to give you a revised probability estimate. And that's the so-called posterior distribution. Now, if you want to do Bayesian inference manually, by hand, then very often you need to design a special set of priors that allow you to go through this mathematical mess of turning priors into posteriors. There are these conjugate distributions that you have to find, and people have derived all these things. But then when people realized that Monte Carlo, that Markov Chain Monte Carlo methods could use likelihood ratios, and you didn't have to normalize, you could just sample, it actually allowed people to start using a wider range of priors of different shapes, because they didn't have to end up calculating these true density functions. They just had to have things proportional to them. So it turns out that these MCMC methods give you a lot more freedom when doing your Bayesian inference, because you can use a wider range of priors, because you don't actually have to normalize these priors and normalize the posteriors. And you say, well, then what's my output? Like, normally in a Bayesian problem, I'd have some prior distribution, I'll call it FP. I go through, I combine it with data, and then I get F posterior. So F posterior. And so this is a function and that's a function. Now you say, well, what? I don't get a function out of this, I get samples. Well, the idea is in an MCMC, I'm going to generate 1,000 samples, take a histogram, and the shape of that histogram will be my posterior. And then I could fit something to that, for example. And then that's the way I get around that. So it's a numerical way of getting these posteriors out, but it allows you the ability to use a wider range of priors, all because you don't have to normalize. So that's the beauty of this Metropolis Hastings, and now all the other MCMCs that make use of likelihood ratios, is they get rid of this ugly normalization factor, or the partition function, which the physicists like to talk about with the Boltzmann. Yeah.
I didn't get it. You're talking about not using a distribution that sums up to 1. Is that what you're trying to say?
Well, I'm saying that normally we know that a PDF has to be positive, and then we know it has to be scaled so that it adds up to 1. The integral adds up to 1.
Yes, and then in Bayesian inference we use such distributions, and
Right.
then we reshape it with on the basis of the priors, as you just said.
Right.
And so what's gonna happen when we have a distribution that doesn't sum up to one and we keep on doing it continuously?
Well, no, what I'm saying here is that the histogram you get out of the sampling, that histogram is going to add up to 1. It has to, because you're just taking a frequency distribution. But the idea here is that it turns out that you need the full proper form, everything integrated out, so all the sort of nuisance variables integrated out, and so that you can properly normalize each one of your density functions in order to sort of handle Bayesian inference in the purely mathematical way. But this numerical way says that the tedious task of taking an integral under a really ugly density function. So it might be that this density function, you remember X is multivariate. So this is like a joint distribution that might be over like 10 different random variables or 100 different random variables. And I might be able to calculate every single density in an instant. But if you actually want me to normalize this thing, I gotta now take a numerical integral under this. And that integral, again, is over like a 100-dimensional space. And so I can get rid of the normalization, and I can just say, don't normalize your density, because I'm gonna divide it by another density anyway, and it's gonna be all the same. So the fact, I'm not saying that we are using illegal density functions, but we just can skip the step of normalizing them, because everything gets normalized through the likelihood ratio, because you're dividing one density by itself. As opposed to other Monte Carlo methods where you really need the density to integrate under to 1. And so here, the density, you only need to know the shape of the density. And that's one of the benefits of these MCMC methods.
So like if we sum out some of the variables of the prior, so is it not gonna sum up to 1? Is that what you're trying to say?
Well, I guess, yeah, I'm saying that if you have a cool prior that you would like to use, you don't need to actually go through the process of normalizing it to turn it into a real distribution. It needs to be, at least, it needs to be a real distribution. Like, in other words, like you could, in principle, have gone through that effort and it would come out and be a real PDF. But as long as it is proportional to a real PDF, that's all you need for the prior going in.
And it's just acceptable to be any other value other than 1?
Well, or the integral underneath this could be anything, because you end up not using it for anything, because all you really care about is, well, is the next point more likely than the previous point in terms of likelihood ratio? And because of that, this doesn't have to be normalized. It just has to be the right shape. And then it will then properly sample so that your posterior, now when you take the frequency distribution across the posterior, that of course will be a real PDF where everything will sum to 1 and everything just like you like it. But you don't have to go through the numerical effort of integrating under this. And that's one of the benefits of MCMC. All right, so that's Metropolis Hastings. Nothing really nature inspired, except it was inspired by the original Metropolis algorithm, which was effectively, Metropolis was looking for in MCMC to draw from the Boltzmann distribution, and then Hastings realized that's what Metropolis is doing and just generalized it and put that F in there. And so we want to try to get back to the kind of physical side of things. Let me just make sure that's all, yeah, I think that's all I wanted to say about Metropolis Hastings before we can now jump over to simulated annealing. So we have this, and we like to use this to improve. So 1983, we have this paper comes out from Kirkpatrick et al. I think it came out in Science of all places. Yeah, Science. And it is optimization by simulated annealing. And so there are 4 ingredients that we need in order to do this. And so we need a concise, so this is how Kirkpatrick defined it. He said we need a concise description of the system we want to optimize. We need a random generator of moves, rearrangements, and we need a quantitative objective function. And this so-called annealing schedule, which we'll get into in a second here. And basically, all of this was his sort of long way of saying that what we want to do is build a local search algorithm that will start in any particular place and will move in kind of the best way to the next place to search, given a particular budget of how willing you're allowed to let the algorithm step away from a known good spot. And so this is where this Boltzmann distribution comes out of play here, is trying to remove bias from local search. So this is sort of my interpretation, which kind of comes from the kind of Janesian interpretation, J-A-Y-N-E-S, the physicist. The Janesian sort of information interpretation of what's going on here is that we want to say is improve stochastic local search by ensuring steps are least biased. And so this max int idea comes up. And so we give a single constraint which is available kinetic energy. And then we allow the optimization objective, given within that kinetic energy, what is the least biased way you can walk around an optimization function. And then over time, we suck away the kinetic energy. So then we lower energy over time. And the thought is that this simulates how natural systems find minima. How if you have a marble sitting on a rough surface, if you jiggle that rough surface, it'll eventually roll downhill and then stay at the bottom of the hill. Yeah.
How do you handle lowering the energy over time? Because I'm just not understanding, is that just an arbitrary definition?
We'll show you that. We come up with this annealing schedule, which is, it's sort of a heuristic schedule for how you cool the system slowly enough to make this happen.
Professor?
Yeah.
The very first step, concise description. What exactly is a concise description?
A concise description of the system. You know, I was actually hesitating when I wrote that because I don't remember what the hell he was talking about. Because you need an objective function and you need a random generator. So I think this. Yeah. So to me, I would focus on without me going back and reading the paper. This is why I should review my notes before lecture. But these are what I sort of view as you can specify a random generator of moves, which is that proposal function we'll see. You need an objective function and you need a way to cool down the temperature. And so this, I think, concise description of the system, I think, is his way of saying the Metropolis Hastings algorithm. So let's see what that. Yeah, sorry.
So when you say by ensuring that the steps are least biased, I'm not able to fathom what's going to make the steps biased in the first place, because you're going to have a random generator of moves.
Right, yes. Okay, so the idea here is if I am sitting in configuration space, I can move in 100 different dimensions. And so the question is, you know, I could, like, already I'm sitting at a particular point, I can evaluate this point. I say my optimization objective is this value right here. So the question is, where do I go to next? Now you could come up with lots of different ways. You could say, well, you know, we always go north until we get a decrease in our objective function, and then we go east or something like that. And so, but then the question is, like, why is that a good search strategy? So what Kirkpatrick was saying is, can we borrow this from this idea of maximum entropy to sort of say that if your only constraint is that you sort of have a kinetic energy budget which provides you a barrier for how high uphill you can go, then is there a way we can sort of maximize the entropy subject to that constraint so that we can, there's no criticism of us like having a north bias or something like that. So we want to remove our biases as programmers from the thing so that we can draw from a distribution that the only bias, the only information that we are reflecting is the temperature of the system at the time.
So basically what even this is doing is initially it's going to do a lot of exploration because the kinetic energy budget is high, but as and when you suck the kinetic energy out, it's going to settle at one point where you get kind of exploitation.
That's right. So this budgeting, how quickly or slowly you cool the system is going to be very important. But within temperature levels, then the idea would be that you are kind of moving in the best way possible to cover that space. And then hopefully you move into another good spot, move in the best way possible. And then gradually, as you reduce the energy, then you end up settling down, always moving in the best way possible subject to the budget that you've been given. Yeah. Question?
So based on this algorithm, if your goal is to get out of the room, right? But every time you're moving a small step, that you regard as being more optimal. So I think you could end up spinning around in the room forever, right? Without finding the exit. Because every single step you think you're better than your current step. But you just go around forever in this room.
Well, I mean, what would be your objective function in the room?
Final objective is get out the door.
Well, so that we're sort of assuming that our objective functions have a little more convexity. It's true that if that objective function is like, am I at the door or not? Then it would be 0 here and 1 there, and it would be flat here. So I sort of have no information. So the only way I can find that is to have my temperature be so high that I know that if I leave my temperature in a plane, I will find that door in finite time. Now, we won't always be in a plane, but most of the objective functions that we're going to be talking about here have a little more convexity than that, so they provide more information. It is a very difficult problem if you just have these steps, and that as I move here, I don't change at all. As I move here, I don't change at all. Because you're right, in that case, this likelihood isn't going to, it's going to be just as easy to move left as it is to move right. But most of the functions are going to have a little more curvature to them. Yeah. Okay, yeah.
If we can use the terms of genetic algorithms, can we think that concise exponential system is kind of the xenotypes of the solution, and then we can think of random generator models can think of them as a crossover function or the mutation function like that?
Yeah, absolutely. In fact, that is a great segue to my next little steps here.
Oh.
As I show. So let's see here. How does SA work specifically? Then we define a decision variable as the position of atoms. So atoms are jiggling constantly, just like your decision variables can move. A solution is the kind of state of the whole material or whole substance. So the particular snapshot of wherever the atoms are at that point, if you've frozen them, they've gone to absolute 0 and all motion stops wherever they are. The fitness you can think of as the energy of the substance. Although people say that, I don't like that definition quite. It's like, I guess it's sort of like the potential energy of the substance. We can kind of get into the sort of philosophy of it, but.
K times T term?
Huh?
Is it gonna be the K times T term?
Well, we'll get to the KT stuff here in just a second. Because that's important, but so this energy, this fitness is really like my fitness objective. And so whatever the thing I'm trying to optimize, my big F. My initial solution is random. My selection function is my acceptance function inside the Metropolis Hastings algorithm, and then the process of generating new solutions is the sort of movement of atoms. And so this really is a local search algorithm in that we are basing the next position on the previous position, and it's kind of like atoms are constrained that they can't move that far as they're jiggling around from their previous position. So it's different than a genetic algorithm where you potentially could jump all over the space. You're kind of constrained a little bit, but that's really meant to be this kind of local search. You're kind of searching locally. All right, and so this acceptance function depends on the temperature. So put underneath here, depends on the temperature, whether we accept a point. And so here's where all that max int stuff comes into play here. And so if you remember, the way the Boltzmann distribution works is you say, I'm going to hold the temperature of this room constant. And so if you hold temperature constant, what you are effectively doing is constraining the available kinetic energy for every molecule in the room. And the translation from temperature to kinetic energy is this Boltzmann constant. So for physical systems, that's why you see this KT show up all the time. And so KT is the kind of mean kinetic energy available to individuals, I'll say. And so in optimization sense, this is going to sort of define the maximum, or at least on average, the average barrier height that you can cross at the current temperature of your simulated annealing. And so if we view the, so if we draw kind of an optimization function that we're trying to find the minimum of, then if we're sitting at some particular point here, then in order for us to find this minimum, we need to be able to get over this barrier. And so we provide, this thing's jiggling with thermal energy, and that thermal energy is, so that's kind of like the temperature gives it this much jiggle, and that's going to translate into enough fuel to get over this hump or not. And so this KT actually kind of defines the maximum height that you can get over from any particular position. And so as you cool the system, what you're effectively doing is committing to little pits in this optimization objective of a particular depth. And so simulated annealing basically gives you enough energy to jump out of any hole initially, and then gradually starts reducing that energy so that you get stuck in holes of sufficient depth.
And,
Yeah.
and how many of those, so you're starting with a random number of points, and how many of those points actually cross the barrier depends on how much of kinetic energy.
This is not a population-based algorithm. You could certainly build population-based algorithms, but they sort of, I think, run like this in parallel. So just picture one point, and what you're going to do is you're going to allow that one point a certain number of moves before you cool it down. So you get 10 shots at this temperature, next temperature, 10 shots, next temperature, 10 shots, and so on. Until hopefully, when you gave it enough energy, it went all over the place and then managed to maybe hit this wall, and then you cooled it, and then it got stuck in this trap here. So that's our constraint. Given you can move up the optimization objective this much, then move in the least biased way within that window of constraint. And so hopefully you then uniformly kind of spread out as much as you need to find any other barriers that you can get over. Yeah.
So at the beginning, you want to be able to theoretically get over any potential barrier to reach the next possible.
Right, you set the temperature high initially,
Yeah.
and then it basically, it basically just takes whatever random solution and just re-randomizes it. And, but then eventually you gradually turn that down, and then you start interfacing with this potential energy function. So yeah, that's, you kind of think of this as kinetic energy, and this is potential energy. And so do I have enough kinetic energy to get over these potential energy humps? Yeah.
Professor, you say least biased because let's say you're standing at that point and there is an option to go either left or right, and let's say left utilizes 2 joules of energy and right utilizes 5 joules of energy. You are going to choose 2 joules of energy, right? Because it takes minimum out of a kinetic energy reserve. Does the point do that?
Well, so we'll see. I'll write up how that energy gets into play. It's kind of like, it's more of, if I have 2 options that are both 2 joules of energy, then which one do I pick? And I want to kind of guarantee I can go either one of them in equal probability.
So it's like each and every point is going to be considered equal when it comes to energy expenditure?
Well, no. So just give me a second, and I think that we'll answer that. But effectively, it's going to be harder to get to this point as it is to this point, even if they're the same distance away in this space. And that will come into play here. Is that we'll see exactly how it comes into play here. All right. Any other questions about this interpretation? All right. So so the acceptance function that depends on the temperature is basically, so this is the probability. So given that I'm in point X, and I want to go, or I'm thinking about going to point X new, then, and this should remind you of what happened in the Metropolis Hastings, a 1 if the optimization objective at X new is less than the optimization objective at X, and then otherwise it's e to the minus delta f over lambda. I'll just say otherwise. And this lambda here is our temperature, so it's kind of like we're saying KT with K equal to 1. So we don't actually need a real Boltzmann's so we just assume that it's a 1-to-1 trade-off between temperature and energy. But you can still view lambda as a kind of potential energy height that you have to get over. And that delta F, in case it's not clear, that delta F is going to be equal to F of X new minus F of X. And so this is where this energetics comes into play. And so that if you have to go way, way, way uphill, then delta F will be very, very high. And this will be very, very low because of the negative. And so it's unlikely that you're going to make that jump. But that's why we've got this little divided by lambda. So initially, if lambda is large, it permits huge excursions. And so this really can be viewed, again, as the kind of kinetic energy you have to surmount potential energy barriers. And so given that I've given you this much budget, I am then saying, but the rest of what you do, as long as you stay within that budget, better be the least biased way you move around. And that's why we've chosen the Boltzmann distribution here. So this is effectively Metropolis Hastings, but we are sampling from the Boltzmann distribution, just like Metropolis originally did. But instead of using an energetic landscape defined by, say, gravity, we're using an energetic landscape defined by our optimization objective. So we are atoms jiggling around in a material whose energetic states within that material are defined by an optimization objective. But our jiggles, our local jiggles, are governed by the Boltzmann distribution, so that if you took a histogram of kind of the energetics of what if you looked at for any given temperature, if you looked at where your simulated annealing algorithm was and evaluated your optimization objective in terms of each one of those different points, you would get a Boltzmann distribution of your optimization objective. So you're sort of settling out in these energetic states. So that's our acceptance function. So this is, I guess we'll write that as our acceptance function. And then that right there is effectively sampling moves from Boltzmann distro. And so a lot of people will come up with philosophical reasons for why the Boltzmann's distro is a good one to use. And there might be good reasons for that, but to me, the most fundamental reason that you can come up with is that is the max entropy distribution subject to a single energetic constraint. So if you simply are saying, I'm allowing you to go up this much, but no more, then this is the max entropy way to do that. That's why we choose the Boltzmann. And anything else to me is just icing on the cake, any other explanation. It's all about max int. All right, so that algorithm, so okay, then yeah, how do we then deal with the annealing schedule? So annealing schedule, this, you have a lot more freedom with this. And the best annealing schedule is going to probably depend on your optimization objective. And so you can imagine changing this temperature over time. And so you could imagine a bunch of different options. For example, you could say, all right, I'll start with some initial temperature, and I will then decrease with time with some linear constant. Or you could imagine a different schedule where maybe I've got my initial one and I just do some alpha to the t, you know, and then you can come up with other ones. So here are like two kind of common choices: just decrease linearly or decrease kind of geometrically. Yeah.
Is going faster or slower kind of trading off between exploration and exploitation? We talked about before, or is that just not related?
I would say it's trading off between speed and accuracy. So, yeah, so I would say there's a, so there's a speed accuracy trade-off here. So the higher you keep the temperature, the more sort of just you're going to be exploring. You're right that you are switching from exploration to exploitation. You want to give yourself enough exploration. But I guess the idea here is that if you did give yourself an exploration, the hope would be that you'd have more accurate solutions. So I would say that really the cost you're paying, this is sort of a better captures what's going on. But you're right that when you're in high temperature mode, you're exploring, and when you're low temperature mode, you're exploiting. So I guess I could maybe also say exploration, exploitation. All right, so let's then write just a quick pseudocode for how to incorporate all this, just to make it clear. Yeah?
There are, so this takes care of the temperature. What about the second variable in equation, the total available budget? An elite schedule does not take care of that?
Well, the temperature is the budget. So this right here, these are the, so there's only one parameter to worry about, which is this temperature, and that temperature is set here. Now you have to determine this parameter, but that's kind of up to you.
So when you say that so let's say I give you a budget, let's say 50 joules of energy, and I have temperature at let's say 100, and using which you can, within the 50 joules you can jump higher. So
Well,
I can keep those 50 joules constant and bring the temperature to 50 so that you can still, the jump is lower, but you can still move around much.
Well, there's only one degree of freedom. You can't give me both a temperature and an energy budget. The temperature is the energy budget. So if you were to say you're at, like there's a conversion constant of K, which converts from Celsius to joules. But we just kind of assume that they're the same units here, which is why we kind of set K equal to 1. So when you set a temperature, you're setting the budget directly.
Okay, so what you're telling is it's not only the jump height that I'm reducing, but also how much you can move around. Both of the things are reducing at the same time.
Well, I would say that you're not directly limiting how you can move around here. I mean, you are in your proposal density function. So you have to come up with this, like if we go back to Metropolis Hastings, you need this move generator, which is this Metropolis Hastings is back here. So I need this move generator, so I need to set this variance here. So that's a free parameter you could put there. But whether those moves are accepted or not is kind of everything else. And so this is not directly limited by the temperature, but it sort of is, because if you jump far away, then it's likely that you're going to jump far uphill, and that's going to be unlikely to be accepted, and so you're then going to be rejected, and you're going to stay back here. Okay. Yeah. And then I'll. Go ahead.
Because this simulated annealing just consider the actual, based on the actual physical annealing. So the function around the temperature is always decreased. But is there any variance considering the certain cases that increasing the temperature like that?
Well, I mean, you can definitely come up with adaptive annealing schedules.
But is there any cases consider that the temperature increased cases like that?
Well, yeah, I think you can find examples of annealing schedules that do try to use history in order to kind of bleed energy back in and then take it back out and then bleed it back in. So yeah, you can imagine, effectively this is like a step size in stochastic gradient descent or something like that. So any sort of intuition you have about adaptive step sizes, where sometimes it gets tiny and then they get bigger, you can apply the exact same logic here, and people have.
Is the lambda not the temperature?
Lambda is the temperature. So lambda is temperature. That's just in the particular text that I've linked on, that's the variable they use for temperature. And I just don't call it T because technically it's KT, but yeah, you can just, it's just temperature.
Also, shouldn't alpha be raised to the negative T to like take care of the dissipation?
I guess I was assuming that alpha was between 0 and 1. And so as T gets bigger, then this shrinks down, yeah. So, right, so you could come up with different alphas and, yeah. So, dot, dot, dot. All right, so general essay pseudocode then. So so let's generate an initial solution. Call it, if we want, we can call it x0. Evaluate fitness f of x0, which you can kind of think of as the energy, the potential energy of that configuration. And then we're going to have a constant, well, I'll call beta here, which we can think of as the number of moves at each temperature. And so, while not termination condition, so whatever termination condition you like, you could do this based on convergence criteria. You can do it just based on number of function evaluations, whatever you like. Then it's pretty simple. You just, for j is equal to 1 to this beta parameter, generate new solution. If better in terms of f, keep. Otherwise, keep based on Boltzmann likelihood. So this is just that acceptance function from the previous page. And then you just iterate that for those b times. And then after that, you decrease the temperature a bit. So decrease temperature. And that's just your lambda update rule, whatever that is. And that's it. So it's start with a high temperature. So I didn't say, I guess that's another initial condition where there's a high temperature. Give yourself, b bites of the apple, and then try a different apple, and then another bee bites, and so on and so forth, until eventually you hopefully cool down and find a good solution. It's so simple, and yet it's been wildly successful. It's like a really good meta-heuristic, especially for a local search, that's only sort of searching in one particular place. It does, pretty well. And it's the claim that the Boltzmann distribution is what allows it to do so well, because it is kind of provides this unbiased way to view your optimization objective, but eventually kind of settle out. And you could imagine adding a bunch of like memory to it, like oh, remember your best solution so far, and if you've strayed away from it, then come back to that solution, and all those things. And you could do that, and that gets kind of genetic algorithm-y, but like with elites and all that. But something as simple as this works remarkably well just by itself. Yeah.
Did Patrick win anything?
Win anything for that? I mean, the paper's very well cited. I mean, it's really not that, like, someone was going to come up with it, right? It's very intuitive, especially because, I mean, we're talking about the 80s, so this is when NLP was coming up. People already had maxint on their minds, so this was a very natural way to go with maxint in an optimization way. So just take maxint that was being used to predict words and now just predict moves. And that's it. So, any questions about the basic algorithm behind simulated annealing? Is the connection to max entropy clear? That it's, I provide a budget and I choose the least unbiased way, or the least biased way to move within that budget. You could apply that to lots of things. So the budget could be in other criteria that you could put in other algorithms and do something similar. Well, that's the end of this unit, which is on these non-biological inspired. So what we're going to start with next, not today, but next is distributed artificial intelligence, so swarm intelligence. We'll see a lot of autonomous learning systems, acting independently, communicating to share solutions. So we've gone from genetic algorithms, which don't really have any agency, but they're still kind of lifelike, to these things which aren't even lifelike whatsoever. They're just the atoms bouncing around. And now we're going to say, what if we put intelligence on each one of these individuals walking around in the population, and then have them coordinate what happens? And so that's kind of where we'll go with that. So this is where we'll have things like ant colony optimization, and so on and so forth. And so that's what's coming up. But that's all I've got for you today. So if you have any questions, feel free to come up after here. And so now we've hit the end of that unit. I'll probably put together another little homework over these concepts.
Still praying. We good?
It's a startup called so there are platforms where essentially professors / specialists.
Turn this off here.